All right, now we'll talk about something called sound level. How loud does a sound sound to you? Okay, now here's an interesting fact. So actually, I'll unmute you guys all just so. Okay, so for a second, let's hear your answers. Okay, so let's say a violin is playing. Now, so let's say at a certain intensity level. Now, if you want to hear the sound twice as loud, how many more violins do you need to add, roughly? So let's hear a quick answer. 2, 3, so and they'll all play at the same intensity level. So you have one violin playing, but now you want to hear the sound twice as loud. How many violins do you think you need to play to hear it at twice the intense, at twice as loud? Any answers? Any takers? All right, so I'm getting no response.
Yeah, because otherwise, if we came near you, we would have to go to a physician, and then they would.
Okay, so it turns out that you would need 10 violins to play to hear the sound twice as loud. Okay, so that's the amazing fact. And if you want to hear it 4 times as loud, you would need to hear 100. You would have to have 100 violins play. Okay, at the same intensity level. So it turns out that that's how all our senses are. So the perception of loudness is, okay. The perception of loudness is more accurately described by the logarithm of the intensity. Okay, so what that means is, so let me go to, okay, so it turns out that our sense of loudness does not go as linearly as intensity. It goes more as logarithmically as the intensity. Okay, so our sense of loudness increases more logarithmically. Okay, and that's true about all your senses. So for instance, if you eat something hot, you double the number of hot molecules and it won't taste twice as hot. Okay, and so on. Okay, so humans can hear intensities in the range of 10 to the minus 12 watt per meter square. That is the softest sound you can hear. And the loudest sound you can bear to hear is 1 watt per meter square. Okay, so that's a trillion-fold range. Okay. So the softest sound you can hear is 10 to the minus 12 watt per meter square, and the loudest sound you can bear to hear is 1 watt per meter square, a trillion-fold range. So, but of course, this sound doesn't sound a trillion times louder than that sound. Okay. By the way, this corresponds to a displacement amplitude range of 10 minus 10, 11 meters. That is the 10th the size of an atom. So an atom, when it's vibrating like that, you can hear it. And when this is 10 to the minus 5 meters, so that's a million-fold range. Okay. So the threshold of pain doesn't sound trillion times louder. The perception of loudness is more accurately described by the logarithm of the intensity. So we define something called a decibel scale, which for intensity, which reflects loudness more closely. So the decibel scale of intensity reflects our perception of loudness more closely. Okay. And here's how you define a decibel scale. This is logarithm of the intensity. Intensity is watts per meter square divided by the threshold of hearing. I naught is 10 to the minus 12 watt per meter squared times 10. So this is the decibel scale of intensity, which is closer to our perception of loudness. Okay. So threshold of pain is 1 watt per meter squared. We'll come to this graph in a little bit. And has on the decibel scale, it's 120 decibel. So a sound level of 120 decibels is painful. And threshold of hearing is as an intensity of 10 minus 12 watt per meter squared. On the decibel scale, it's 0 dB. Okay. So at 0 decibel sound, you can barely hear, and 120 decibel sound is painful. Now, here's a general rule of thumb. So when sound level increases by 10 decibel, it corresponds to an intensity by a factor of 10. So that's intensity. So that's 1 violin and 10 violins playing. So if 1 violin is playing, let's say it's at 5 decibels, and then if 10 violins play, then it's at 15 decibels. That's what that means. Okay. So as a rule of thumb, doubling in loudness is approximately associated with an increase in sound level by 10 decibels. So for instance, there's a mosquito buzzing, and that's 40 decibels, and normal conversation is 50 decibels. So that's twice as loud as that. This is twice as loud as that. And this is 4 times as loud as that. Okay, so that's how it works. So loudness is a psychological response to sound and depends on both the intensity and frequency of the sound. Okay, so the perception of loudness is a little complex. Now, prolonged exposure to high sound levels can seriously damage ears. So most rock stars have compromised hearing. Noise pollution can be bad to your health. Okay, it can cause high blood pressure, anxiety, and nervousness. Okay, so your hearing, you have wonderful instruments to perceive sound. Okay, and your hearing, along with your processing power in your brain, you can gather a wealth of information such as pitch, loudness, and direction. So you can figure out the pitch of the sound, the loudness, and where it's coming from. Your perception of frequency is quite good. So frequencies that differ by 0.3%, you can tell them apart. So for example, a 500 hertz sound and a 501.5 hertz, they're different, noticeably different. Okay. As far as loudness goes, you're able to discern about 1 dB difference. And a change in intensity level by 3 decibels is easily noticed. Okay. Okay, now your sense of loudness and decibel scales are not exactly the same. Okay, so when you go to a doctor's office and they check your ears for loudness, see these curves known as fawns. This is 120 fawn. So, and this depends on the frequency. So for all these different frequencies, that's 120 decibel level. That's what an instrument would measure. Okay, that horizontal line. Your ear would measure. So at this frequency, your ear would need 130 decibels to sound like 120 decibels. That's what that curve means. Okay. All right. So this white area is what you can hear. So at low frequencies, The sound has to have quite a large decibel level before you can hear it. Okay. So you're most sensitive to about 3,500 hertz. Okay. That's where you're most sensitive to. And you, of course, don't want to be in the non-white region. Okay. Frequencies greater than this, you can't hear. So bat use these higher frequencies to echo, locate, and so on. Underwater communication sonars use high frequency sound waves. And they also use at the high intensity levels. Okay. Okay, time to pause again because we are moving on to a new subject. So I will